Numpty. Go to proof now. So let's try to do this. So basically, I got it. Basically, the radio sonar system. Basically, the sensor system. I got the proof here. We got the documents here. Basically, I waited myself. But I'm gonna start. It's all organized. Okay. So where do I start? So you got the rotation of hexadecimal 0 to F or F0, which represents all the color set from 0 to F and 9 to 0 to F or F to 0 times 0. And you get 90. So you get 10 to 15 for A to F, and now be 90. 90 innumerable states of homogeneity and inverse conjugates as well. So you get so the goal is here to define I got the proof here. So this is the proof here. I got it for the radio system. How would it work? So I'm not joking because basically the radio system works on Hamiltonian 11 resolution. So basically what it does is like use the thing called a Cisco table to do it. So basically the radio channel, let me just find it again. I'm just shuffling paper because I don't know what I'm doing. So basically you got the visible light spectrum. So the visible light spectrum. So you get this is a Cisco model of the visible light spectrum. So take notes. Yep. Let me take notes. So that's the visible light. So you get visible light. So you get visible light, and you see you get right root left. Basically this is Cisco. So when you have so you get from the visible light root, you get a red and the right. So you get when you get you start seeing red. So visible light red. So red Roy GB green blue. So I have to do it again. So the red is the red. Red is the root. Red is the root. Which is start visible light, and then a red right, and you put one on the right, red orange, and you go left, yellow, red orange yellow, indigo, then you go right again. That'll be Roy, green, and you go green, then you go indigo, and then you go violet. So you get red, green, red, orange, indigo, violet. Red, right, left root, right, left root, and then right. Oh my days! Stop. Indigo, violet, yellow, indigo, and violet. So you get the left node indigo is from the yellow, and violet on the right. So you get indigo, violet. So basically this table here. So you get the model here, this current model here. So you get here, so you get root is red. So basically it's Cisco. So Cisco packets are in red. So before I dive into that, I got the coil packets. Basically, the coil packets work on the IQ principle, or it's for faster communication, faster hops. You take. I'll come up to that later in another video. But I have to write down coil packets, trident packets, coil trident packets. So basically, you get pi r squared. Now pi r squared is like the area. So for example, the screen is we have it's 10 pixels, 1080 pixels. That'll be 1080. That'll be using the 4 to 3 ratio. So you get out 3 colors, 5 4, 3 red GB, red cones, blue cones, red green, blue, model of color. That's 3 red, 3 colors. So that's 3, 1 2 3, and that will equal 1 color, 1 pixel. 1 pixel. Now 1 pixel space is either it's only it's a bound by area. So the area of 1 pixel is pi r squared. Now pi r squared. R squared. So that's times 360 times 660. Pi squared over 180. Now 180 represents some kind of baseline between the start and stop. Between the radius. So basically the radius is 180. The radius is half. The diameter is A to B. This is how so usually radius is 15 pixels. You get 180. So saying it's a pi model. So you get pi r squared times 360. So what I've done here is give you an example here. So basically 0 to F. For example here. Okay, so you get the visible light spectrum. So you're gonna get map the radio with the visible light spectrum via the digital waveform. So we're trying to get read only digital waveform via Hamiltonian linearization. So basically, you're trying to literally just polarize all the sound out, not even out and in, and you don't polarize the noise out into sound. For example, you So we get derive an area function. So we get something called the OBINexus differentiation function. So let me give you an example here. So we get E star. So again, we get so I don't know what's again because I read booked the one here earlier. So we get 2 pi r. So if r is 180 pixel, then pi r is I mean r squared. R squared is because if the radius is 180, the r squared is r times 2100. So if the radius is 1080, the radius squared is 21,000 times pi 3.14 is 6.6 or 647.16868 centimeters squared for display. So basically, there's no color there. The color model or RGB are literally distilled, into the pixels. You see what is there, based on the room, but basically what it's showing. There's no like a blind spot. You can't pick up because the video is detected. So that's like there's no blind spot. It's not like basically you have something that doesn't it's not half model. You have the full model because it's distilled. There's essence in it. It's full, but you see what is there, in the fullest, basic model. I got this here. So I could just look at an example instead, but I already got an example. I think my example is too scattered here. So back to the thing. So we get the interdependency model. So for example, we got the right see this is the waveform here. So you try to get the digital section out of analog. Basically there's an analog channel. So the analog channel is there. The analog is like the analog channel. So analog is like the standard channel that everyone that's noisy, and you get the digital channel what we get interpreted, what we get in the system. So the concept of hops. So basically you get Hamiltonian and illustration. So we try to get one-to-one mappings from system of analog. So we get a system of one algorithm or analog system. Yes. So we get something called Hamiltonian. Hamiltonian is like Hamiltonian based on the Cisco model is a stack-based structure. So it's a first in, last out. So anything you put first goes out first. It can be a row or column of binary. So if you have a row of 0 and then a 1, the first thing to go out is 1 and 0. So that's that one. But that's how our stacks work. So if that's the model of a stack using Hamiltonian sync. So you can't even do with a cube, but you can sync it with the 11. Basically, the 11 does the same thing, goes the other way because it works in edges. So the edges are the Hamiltonian nodes. So it works basically equates the kind of structure. So it's like you have some kind of bipartite resolution between Hamiltonian. You can use to create a better distilled image based on your CYMK, cyan, yellow, magenta, and the chroma key. So that's it. So I think I've just worked on for you guys in real time because I've lost it my track myself. Let me just do it. Let me just do it again because I don't wanna start. I'd rather do that and because everybody worked out and I got my calculator here, so why not? So get everything here done. So again, we have Cisco. Cisco is like Cisco root red. Red is root right red mic red orange Roy G B B. So that's Roy yellow, and then right again, which is orange yellow, and this is royal indigo blue Roy yellow indigo bravo G green yeah blue violet indigo and violet. So basically red orange yellow indigo white green blue indigo and violet. So to get our model here, so you get so we need to pick out to see orange. I'll go from red. I go 2 hops. So orange is let me just say blue. So I get blue. To see blue, I have to the key of blue. Only blue colors I see. I go hop. I have one hop left. One left up left. I go left. 1 2. two left hops, L2 or 2L, based on the model. And then I go to next now we come up red, and then wait. Oh, sorry, no, that's wrong. So this one hop left and one hop leave. So to see blue, Richard of York, Orange York, gave battle. So R O Y.
Mr. Namdi, can
Yes.
turn off this light?
Green. No,
This one?
no.
This one?
No, fine. So for me to see blue, I go two red, and one right and one left. So two left and one right. So that'll be the blue color. Blue is in this spectrum. Row conjugate. The conjugate will be 1/2L, and that'll be 2R 1L. So basically 2R 2L 2L 1R is 2R 1L. Basically, this is just the Risco model. So Risco model gives you the whatever on the other side, inverted. So it works in Cisco with Risco, and you get the color spectrum. So this is called hops. So you get one. We use called hops basically. Hops the channel. So half the spectrum, half the channel. But the channel is this whole spectrum, which is your operational. You can see. So you get the radio. So you get the radio wave model, which is like radio wave, microwave, infrared, visible light, X-ray. Rent money is visible under X-ray glasses. So get rent money visible. So get the root node is rent, which is radio wave. So radio wave starts. So radio. So you gotta have some kind of mapping between the start and the end. So every kind of so radio wave. So rent money. So for me to see the visible light, with the visible light, I have to go through the same state I was in. So this tomographic mapping. So you get some kind of clamp, so some kind of sparse structure that they can do. So the radio wave will be. So for me to be to see the radio, I have to have my radio wave to measure digital form, like some kind of digital equivalent of visible light. Based on so you get radio wave, and there'll be two hops left. Two hops, two depth. So get if I start 1 2, so radio root, one left, one right, and one right. Sorry, so you get two right, and I'm visible light first one. Wait, sorry, no, that's wrong. That's radio wave, microwave, infrared, visible light. Sorry, radio wave, microwave, infrared. So get two from the root is my root is default to the radio wave. So you get two microwaves. Two hops, you get one microwave, one hop down, and one down, one hop right, and one hop left, and that'll be I'm now visible light via radio wave signals. I'm getting that. Same for the 2L, and that'll be the blue. So for me to see blue, I'll give you some. So me to get the blue colors, the blue hue, I'll have to get some kind of mapping there. So for me to see blue. I don't want to give you all the channel frequency, but I'll try to only calculate the blue channel, see whether it's there. So what will be blue? So after 45, so blue only color will be 2L, 1R, and that'll be blue. And that'll be the same as 1L. Also 2L. 2L 1R, that'll be two left hops and one right hop will be blue, and that'll be red. One left hop, one left hop, and one right hop is blue, and that's blue, and then we get the other one, which is don't fuck it up. So this is why the interdependency works. So we can have an interdependent matrix to do it. We can calculate it on the sparsity. But I want to try the interdependence because it's very easy. So get the hop tree. So get blue is equal to one left hop and one right hop. Based on the visible light. Rent money. Radio waves. And then we get blue. the color blue, and then we get. Okay, let me just make the whole color spectrum. So red is what? Red is where? Red is on a spectrum of So red. So basically red. Red is visible light, which is radio visible light. So basically, again. So get if the visible light, so get the radio set. So basically, we have a mapping of the radio states. Radio is where radio waves. So you have two hubs. So get one right and one left, and that's the chemical state of visible light. So then we get one hub. What's two hubs max? And then we need that. So get the other one, which is like a for the visible light. So that's the radio wave to visible light. And we're done. Now to get all the colors, because we can use red. Now red is visible light. So we get from red. So we need red, green, blue. Red, green, RB. So get then do only red, green, blue for now. So to get a red, we get visible light. So we use it Hamiltonian visible light. So visible light will be red. So red will be the fastest. That'll be like one. No hop needed. No hop. No hop. And then we get red. So we get red. So for one hop we need green. Red, orange, green. Bristol of York. Okay, so you get to see green, you need two hops left, hops left, and that's green, equals to green. Blue you get red, green, orange, two hops left and one right hop, and that'll give you blue. So you get that one. So you get the model here. So no hops, you're only seeing red. You only seeing red and everything. So basically, if you want to do this, so you get hop off. So you get one hop. So you can have no hop, and iota state, different state. Now you only see red. But that red is like a hue of red. The shift that's basically bouncer is like you don't need to hop anymore. So that's no hops. You get no hop. So no zero hops. You need for red. So the idea is this. So now you get so basically you can have the Hamiltonian graph through this. So you can have Hamiltonian start and stop. So you get Hamiltonian two Hamiltonian pairs. Hamiltonian start A start A end A start Hamiltonian visible light V start Hamiltonian A start A end. So get A start or end and A start and end. So basically get A start and end. You see the A represents the start. You get the middle ground. So the middle ground is where the particle was in the polar pi r squared. So the goal is this start. So get Hamiltonian, which is like the second one. So Hamiltonian will be a bottom up top down search. Top down, but I prefer Illyrian. So you don't really so because we don't really need Illyrian. We don't need Hamiltonian. This is my data here. So that's why I need. So we need Illyrian. So how would this work with Illyrian graphs? So the structure holds because Illyrian better because I don't use Hamiltonian. I make a mistake and break it. So you can do some math on the pi structure. So you actually do the math. Let me get the math down. So you get the pi here. So you get here. So you get this here. So you get this here. What do we get this here? What do we get here? So we get this here. So you gotta get these pi from so red, we should have York, okay. Red one. So you get again. So you have to get the pie to do it. So once again, I just got my paper. 2 hops left, one right, and that'll be yep. So red green. So get 2 hops to red. So you get no hops needed to red. Based on no hops to red. To and they get this thing. I don't do it again. I just have to rewrite it down again. So you get red. So get no hops to red because you're already on the visible spectrum, and that because you're already been at if you're already on the channel, 1 hop from the radio wave, 2 hops and 1 hop from the radio wave, right, and 1 hop left. If you're in the left section, and you get let me see how to compute again. So you get red. So again now to get you get you get 2 hops. So basically, I use all the color spectrum. Red is what red is nil. Now to get 1 hop 1 hop for red, green, 2 hops left for orange. You look red for the green, and get blue. 1 hop left, 1 hop left, 2 hop left, and 1 hop left for green. For orange, and 1 other hop left for green. So that'll be green. So that'll be the way you're gonna get to see whatever the spectrum properly. So you have to use the Hamiltonian start and end based on the pi r squared to do it. So pi r squared will give you, if you're using like let's use like a pixel 70. So you get the pixel 4 3. So you get 3 pixels RGB. The 4 pixels so you get 1080. 1080 divided by 3 is divided by 7 basically. Divided by 3 3 will give you how much pixel you should store. So 10, let me do my calculator now, because you're only working with that ratio of 1080. You basically need to divided by 3. That'll be, every pixel will be 360 pixels. So you get 360 pixels to store red, green, and blue. Not 225 pixels to store red, green, and blue. And that'll be 360 per 4 channels. For every 4, there's 3 basically. This one represents all the color of red, green, and blue. Of the hops you have done already, you can see in the channel to see what the radio is. And what you're gonna do is have the 11 graphics of it. So how do you do this now? So 11 means fiscal. So 11 means like a bottom up. So if I start with the green, I get green indigo. But I'm doing map green indigo to blue. So green, blue, blue, and because I'm building bottom up pass on green, blue, and Bishop of York gave battle. Green, blue, and yellow. So you're gonna have the G. So if you see green first, if you see, then blue, and then yellow, because this will be Hamiltonian. This will be 11 cycle, because it's starting from the bottom using breadth search. Or first in first out, but for the 11 Hamiltonian one, that'll be Hamiltonian one will be top down, will be red, green, blue, green, blue. So 11 is green, then blue, then green, blue, red. So green, blue, red is 11. For Hamiltonian top down, it's red, green, blue, and that'll be how it looks. So process. So the goal of this is to use the hop system to give the color quantization algorithm. So what is quantization? So my definition of quantization is so you have some kind of mapping gradient. So let's say you have an addition channel. Basically all the channels are share a ratio of 0 to 260. But 0 to 260 has a ratio of 1. So you can map it all to 0 to 1. So quantization is like the depth. The depth. Basically you can control the color the depth of color based on the you can see, you can tune the color, basically tune color, see how much you want to see, how much you want to see, and that's what. So basically, if you tune the color quantity of the color, you have the ratio map. Just to get every color gets 260 divided by basically 260 equals 100%. So we can have like a color of 25%, 25 over 260. That'll be the ratio. This color will be a color ratio of all the mapping. So that'll be the color you get. So 260 divided by 25. Basically, you get 25. Let's say 25 divided by 360. That's 0.4. Now 0.4694 is the ratio of a color that's there. So basically, three colors 360 equals to 360, which is for full set, for the full color set. But you get the other channel, the 4 other channels that are not used to display. So you can use this one to represent the colors, and you can use the other file to display the full screen colors. So you can map all of this 3 to 360 out of the pi. So you get pi r squared area of 360 2 pi r is 360. Basically, you can use the count it. Okay, so you can have 0 or 180 to 0 or 180 to minus 180, which will be the color of the system halfway. So 0 180 to 180, that'll be 2 pi r. That'll be the way the system goes. So basically, you are mapping the colors. So for example, what color would I want to use? Okay, basically 25 is not really necessary here, so it doesn't make sense. So again, I use them. So it's basically polar system. So again, I have the area. So 2 pi r is the area, is the parameter. So 1 is the area. So the pi squared. So I use pi squared. So if I do pi, my radius is what? 260. 260. That'll be my radius of the pixel. The pixel is 1080. My radius 10 divided by 4 gives you 1 pixel. 1 pixel. 1 unit square. 1 unit square. So 180 divided by 4 will give me one quadrant of the pixel, and that'll be 270. So 1 quadrant is 270 area. Now 7 squared. So this is one area. So if I now use half this into the radius, so 240 is a unit. So if I use OBINexus, if I create a if I times minus divide plus, so if I add 270 to the power of 1, and then divide by the ratio. So if I divide by a ratio of 3, because the 3 colors, we get a quadrant. 270 by 3, that'll be 90. So in the 90 quadrants, 90 degrees rotation I need for each color. So this is really one-to-one mapping for full screen. So it works perfectly. So I don't have to do any more transformation that I need to, or have any more rate shift. So for this to work properly, so 90 degrees. So I can use a protocol system. So what I do now is, for me to have a color in space, I have pi r squared or 260. Pi is pi 360 based on radius. So the radius is the unit ratio. So unit pixel, a pixel is 1 pixel. Let's say 10 pixels. Let's say 1 square pixel, 2 pixels, 2 times 4. The width of pixel is let's say 32 by 32 pixels. So we get 32 width. 32 width and 32 width. We get 64 pixels squared. That'll be one screen area. So after this, still autocorrect to that. So that'll be 360. So 64 represents width and height of the pixel. So we get 64 squared. 64 as radius. So you get the 64 pi r squared. So you get 64 squared is what? So 32 squared is what? 32 squared. 32 squared is so you get 32 squared. That'll be so get the 32 times 32 plus times 2. 64. Pi r times pi. Times pi, and that'll be 201.0619. 298 0619 298 8. So that'll be 1 2 3 4 5 6. To system 218 061 929. That'll be 4. And that's the 1 2 3 4 5 6. 1 2 3 4 5 6. That'll be 6. So basically 6 pixels squared. So this represents pi r squared, which is the area it's going to cover. So this is an area quantity. Area the system to look at for the color I'm meant to pick color I'm at. So this area where the color is meant to be, and this area represents the pixel mapped into a color. So this color can be red, green, blue, for all the model there is. So this is the area I'm looking at. This is the pixel I'm looking at, the 2x3 pixel. I'm mapping out to homogeneous. Again, I'm used to see it works because you are distilling color. You're measuring the system. You're not actually constructing it dynamically or with any algorithm. You are learning. You're seeing it, but you are seeing it in real time, on the fly. You're doing it on the fly. There's no exclamation needed, and that's how you do radiomography. Thank you guys.